Namaskar, Adab, Shat Sri Akal. Welcome to the live classes in group theory. So, we have started group theory. We have tried to visualize the intuition of groups. Okay, by using Cayley table and many more things. We have discussed the properties of groups. We have also discussed some problems, and I would like to say, after the discussion of subgroups, it's a time to count the total number of subgroups. Yes, this lecture is dedicated for the counting of subgroups, and certainly the Lagrange's theorem will help you to do it. Yes, Lagrange's theorem. Yes. I would also like to discuss, is the converse of Lagrange's theorem true or not? If not true, then in which condition it is going to be true? And why its partial converse leads to start the discussion of Silo's package. Okay, so certainly we are going to discuss all these things in a proper way. Okay, as you know, I used to discuss the concepts, okay, in a proper way, in a proper grading, and certainly some problems used to come to clear everything. And do you know, this evening is dedicated for the counting of groups. Actually, I would like to say, we are just going to start the counting of groups. Okay, it's just the beginning. So let's start. First of all, I would like to say that before starting this session, I just want to ask a very trivial question, because the trivial word may help you to give the answer of this question. This question was asked in CSIR NET of 3 marks, and there is no need to use the pen to do this question. Yes, if you will use the pen, then you may not okay, there is no need to use the pen, but there is a chance that you might choose the wrong option also if you are not careful. Okay, so certainly what would you like to say about the answer of this question? It might be possible that you are watching it recorded. Then you should pause this video and you should try to give the answer. Okay, so here is what, let G is any group, then G has at least 2 subgroups. Most of the people will, I would not like to say will, but most of you may give the answer as option A, but this is not true. Okay, because people will think that with identity and the group itself, it will have at least 2 subgroups for sure. But the actual answer, the right answer is at least 1 subgroup, because there is a possibility that the group will have only 1 element, that identity only, isn't it? The group may have only 1 element, and in that case the order of group may be 1 only. The order of the group will be 1 only, and exactly I would like to say at least 1 subgroup will be there as the answer. It is not necessary, because the order of the group is not mentioned in the question. So you are free to take a group of order 1 as well, and in that case only 1 subgroup will be there. So if G is a group, then certainly the group will have 1 subgroup for sure. Okay, but you cannot give the assurity of 2 subgroups, because if the elements in the group is only 1, then how can you say about 2 subgroups? Okay, so that's why option A is not true. Option B is absolutely right. Option C is what? G has exactly 2 subgroups. This is not necessary, because if the order of the group is 1, then from where you will try to find the second one? Not possible. So that's why at least 1 subgroup is the right answer. So you can see this question was asked in CSIR NET, and certainly there was just 1 line justification for this question without any hesitation. Okay, now we want to count the total number of subgroups, and certainly the Lagrange's theorem can help you to do it. Okay, the converse of Lagrange's theorem is not true. How can we say that? Certainly we will discuss all those things in this session for sure. But as you know, this is a detailed course and I used to discuss each and everything in a proper way, and by taking those things in our mind, I just want to say that if you have Z with respect to addition as a group, okay, then what shall you say about its subgroups and how many subgroups are possible? Okay, so if you have Z, okay, Z as how? 0 plus minus 1 plus minus 2 plus minus 3, and by doing so, okay, then certainly the subgroups will be of the type this mz, where m is any integer, we can say. Okay, so mz, ma, where a belongs to z. Okay, so for example 2z is also the subgroup of z with respect to addition, 3z is also the subgroup of z with respect to addition, and things like this. Okay, so now let's take any element x from mz. All right, then what shall you say about x? Certainly this x can be written as m into a, where a belongs to z. Once again, let's take another element y from mz. Then in this case we can say what? Certainly our y will be equals to mb, where b belongs to z as well. All right, and we can just think about this, because we just want to prove that this mz is going to be the subgroup of z. So certainly we are going to satisfy the subgroup criteria with respect to addition, and that's why we will do what? X minus y. So this x minus y will be what? M into a minus m into b, and it will be written as m into a minus b. Okay, and this a minus b, if we are just going to write this a minus b as c, then certainly this belongs to z, as this c is equals to a minus b is also an integer. Okay, so that's the reason we can say, so from the subgroup criteria with respect to addition, we can say what? Certainly this mz is a subgroup of z. Therefore we can say what? This mz is a subgroup of z. And as this m is what? This m is what? Integers. Therefore we can say what? Which kind of subgroups are going to be for this z with respect to addition? Certainly this identity group, thereafter 1 into z, okay, which is z itself. Okay, so these two are very obvious subgroups of z, but except these two, there are infinitely many subgroups, like 2z with respect to addition, 3z with respect to addition. Okay, because mz is the subgroup of z, and by doing so, these all are subgroups of z. These all are subgroups of z with respect to addition. So how many subgroups are there? Certainly we shall say what? Infinitely many. Okay, so we shall say what? Z has infinite number of subgroups. Z has infinite number of subgroups. Certainly Z has infinite number of subgroups. Okay, so I would like to say if Z is a finite group and H is a subgroup of Z, then there is a very interesting relation between the order of the subgroup and the order of the group, and that is going to be given by Lagrange's theorem. So let's start this discussion of Lagrange's theorem. Okay, so for Lagrange's theorem, what is the statement? If Z is a finite group, if Z be a finite group, okay, and H is a subgroup of Z, H is a subgroup of Z, subgroup of Z, then what the thing is going to happen? Order of H will divide order of Z. Order of the group, order of the subgroup will divide order of the group for sure. Okay. So, what is the conclusion? What is the converse of this? Is the converse true? Yes, it's not true. Converse of this theorem is not true. I will give you the counter example. But before going to that counter example, we must have to note some facts. Z is a finite group and H is a subgroup of Z. Then certainly this order of H will divide the order of Z. And what happens if D does not divide the order of Z? Then it is confirmed that G has no subgroup of order D. No subgroup of order D. It is confirmed that if D is not going to define this order of Z, then G will not have any subgroup of order D. This is confirmed. But converse is not necessarily true. Converse is not necessarily true. And what will be the statement of the converse? What is the counter example? Okay, certainly we are going to discuss. So first of all, I would like to make a note that converse of Lagrange's theorem is not necessarily true. Converse of the Lagrange's theorem is not necessarily true. What is the converse? The converse is what? If D divides order of Z, it does not mean that G will have a subgroup of order D. Then G need not has subgroup of order D. Okay. So that's why, because you can see this is the converse statement. So converse of the Lagrange's theorem is not necessarily true. Remember, here is Z is a finite group only. If we will add some conditions in this statement, then there may be a possibility that the Lagrange's theorem, the converse of the Lagrange's theorem will be true also. But we have to add one more condition. Only then we can say. So what will be that condition? Yes, many of you know already. However, let me give the counter example for the converse of Lagrange's theorem. Okay, so I would like to say, if we are going to get Z is equals to A4, this is alternating group, and I would like to say we will certainly discuss the permutation of groups. Okay, and in that we will see if we are taking an alternating group, then the order of A4 is what? Certainly factorial 4 by 2, which is 12. Okay, and we know that 6 is going to divide the order of A4. Okay, 6 is going to divide the order of A4 because order of A4 is what? 12. But we will show that A4 has, okay, A4 has no subgroup of, but A4 has no subgroup of order. A4 has no subgroup of order 6. Okay, so these two things needs to be proved. Okay, so certainly I will prove all these things, but before that I have to discuss the permutation group, and I promise certainly we will give you the proof, and we will also mention the statement, the converse part of this Lagrange's theorem. Okay, but for now, as I have not discussed about the permutation group in this course up till now, so certainly we will take, I used to take a special a lecture on permutation group because many counter examples comes from that group. in group theory. So certainly we will give you the proof when I will discuss about S4, A4, their orders, and will show why A4 does not have any subgroup of order 6. But yes, this is a beautiful example, this is a beautiful counter example for the converse of Lagrange's theorem. Okay, so I have told you that converse of Lagrange's theorem is not necessarily true, but what is the condition that is going to be added, and in that case you are going to get the converse is also true. So I am just going to make one more note that, okay, if G is a abelian group, if G is a abelian group, if G is a abelian group and D divides the order of G, then G has always a subgroup of order D. Okay, so here you can see the condition, because in the statement of Lagrange's theorem we have mentioned only finite group, but if that finite group is going to be abelian, then certainly the converse part is also true. Okay, yes. So here in the statement it was only a finite group, but when we are going to mention one more word, then in that case certainly if G is an abelian group, in that case if D is going to divide the order of G, then G has always a subgroup of order D. I would also like to say, when we will start the discussion of Silo theorem or Silo package, then certainly you will be able to see the partial converse of Lagrange's theorem, because when we are going to add some condition, then the converse part is going to be true. Okay, so let's do a few true false that might clear your fundamental concepts. So if we are going to take Z is equals to D4 has a subgroup of order 7, is it possible? Okay, if you are given G is equals to D4 dihedral group, which is certainly non-abelian, so is it possible that this D4 has a subgroup of order 7? Then by just giving a one line justification, you can say that the order of D4 is 8 and 7 is not going to divide this 8, therefore the answer is no from Lagrange's theorem. Yes, I am going to give you another true false, and thereafter I will give you certainly some beautiful questions of CSIR NET. Okay, all right, yes. I would also like to ask total number of subgroups of Z10. Total number of subgroups of Z10. So first of all, you should calculate manually, and thereafter certainly we will give you the formula. Yes, that tangent function will give you the total number of subgroups. But yes, so by using the formula, because first of all I will use the formula and you will understand that how many subgroups will be there, but manually we must write, because this is the very first question, so we must write every subgroups for the clear cut intuition. Okay, yes, anybody can just say the number tau 10 and tau 10 is 4. Okay, but before coming to that one line justification, a clear cut visualization must be here, that why only 4 subgroups are there, why a sense of repetition is there. Okay, so first of all, what is Z10? Z10 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is your Z10. The obvious subgroup is first one is what? Which is going to be generated by 0, and certainly a 0 group. What about H2? Certainly we can generate that H2 with the help of 1. And once again, if you will generate the subgroup of Z10 with the help of 1, then certainly its binding operation is addition modulo 10, and you have to write every element of Z10 with the help as the integral multiple of 1, and in that case you are just going to get Z10 only, isn't it? Yes, it is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which is Z10 itself. Okay, now we will take what? Let's say H3, let's generate it with the help of 2, and in that case you have to generate the subgroup by using the elements of Z10, but generated by 2 only. And in that case you are going to get, you have to write the elements as the integral multiple of 2, and you will not hesitate to say that it is 0, 2, 4, 6, 8. Okay, once again H4 is going to be generated by 3, and in this case what the thing you are going to get once again as the integral multiple of 3, it will become 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Once again you are going to get Z10 only, isn't it? Again the H5 generated by 4, what are the things you are going to get? Once again 0, 2, 4, 6, 8. You can see the repetitions. Okay, yes, you are going to see the repetition. Now for H6, what can you say? Generated by 5, so certainly it will be 0 and 5 only. So up till now, how many distinct subgroups are here? How many distinct? Because this H2 is also going to be repeated. So this H1 is distinct, H2 is distinct, H3 is distinct, and now H6 is distinct. Now if you are going to generate with 6, however you are going to get what? With 6 you are going to get 0, 2, 4, 6, 8, which is similar to this. Okay, so that's why you can see how many subgroups are there, which is exactly the subgroups of Z10. So you can say only 4 subgroups are there. Now if you will write H7, then it is certainly repeated, because it is same as generated by 4, same as generated by 2. So once again, if you are going to generate the subgroup with the help of 7, then you are going to get what? Once again it will be the Z10 itself. Okay, so now the repetition occur, and therefore if anybody will ask how many subgroups of Z10 are there, because Z10 with respect to addition is a cyclic group, and its subgroups will be also a cyclic subgroup. So that's why there should be a generator, and when we are trying to find all the subgroups, then we are going to see only 4 subgroups are distinct, rest all subgroups are only among these 4. The repetition occurs. Okay, so certainly total number of subgroups of Z10 will be 4. But there is a quick formula. There is no need to count the subgroups like this manually. There is no need of doing it. Okay, actually there is a formula, and I am just going to write that formula. But for intuition, for the first question or second question, 2 or 3 questions, we should write every possible subgroups, okay, manually, so that we can get a perfect intuition. But we should also know the formula. Number of subgroups of Zn is equals to tau n. Okay, and how we used to calculate this tau n? Tangent function has been already discussed on this channel. So number of subgroups of Z10 will be equals to what? Tau 10. And how we used to calculate this tau 10? What is the way? We just used to write this 10 as the product of prime. So it will become 2 raised to the power 1 into 5 raised to the power 1. And if you want to calculate this tau of 10, then you just need to add 1 is in the power of prime. So here 2 to the power 1 is here, so 1 plus 1 into 5 raised to the power 1 is here, so 1 plus 1, so it will become what? 4. Okay, so yes, so you must remember this formula. The number of subgroups of Zn is tau n, and you should also write a few examples of a few sets of subgroups as well to make the things clearer. Okay, so now the next question I am just going to ask on this, which has been asked in CSIR, okay, which is a very simple question, easiest question. Okay, so number of subgroups, total number of subgroups of Z100. How many total number of subgroups in Z100 will be there? Certainly its answer will be what? Tau 100. And this 100 can be written as how? 2 raised to the power 2 into 5 raised to the power 2. Isn't it? This is how this 100 can be written as the product of power of primes. And tau 100, if you want to calculate it, then in tangent function only these powers are important, and you just need to add just 1 in the power of this prime, and you just need to add just 1 in the power of this prime. So how many subgroups will be there? Certainly 9. Okay, so these were something that has been started to count the total number of subgroups, and I would like to say tomorrow we will certainly discuss how can we find total number of cyclic subgroups of a particular order. Okay, so we'll see you tomorrow at 8:30 p.m. Till then, take care, bye bye, good night. Okay, so tomorrow there will be a class at 8:30 p.m. and that will be the live class 12. Okay, on this channel already 11 live classes in algebra has been taken, and I have already completed real analysis on this channel. Okay, complete course is available on this channel, certainly you can watch that. Okay, so we'll see you tomorrow. Till then, take care, bye bye, Jai Hind, Jai Bharat, Vande Matram.